Hello, my name is Woo-Jae Kim. Today, I will be giving a review presentation on learning transferable architectures for scalable image recognition, a paper on CVPR 2018. For this presentation, I will talk about the motivation of the paper, previous works, the proposed methods, results and analysis, and conclusion and limitations in that order. There have been many deep neural network models for image classification, and mostly the shapes and depths of layers and hyperparameters have been designed by humans through trial and error. This requires extensive amount of architectural engineering. Thus, this paper proposes NASNet, which is a learning-based model that designs image classification neural network structure. Models designed by NASNet has shown to perform better than SOTA classification models designed by humans. There have been many related works on trying to apply deep learning to generate or fine-tune image classification model. However, they have shown to be not flexible enough, worse than hand-designed methods, or not applicable to large-scale images. Closest to their works was NAS, which also predicts an image classification neural network. However, NAS generates search architectures by predicting the whole network with unique shapes for each of the convolutional layers. This consumes a significant amount of GPU time and memory. NASNet, this paper's work, mainly builds upon frameworks of NAS and improves it for faster and better performance. The paper's main contribution was designing a convolutional cell, which is a group of convolutional layers. Unlike NAS, NASNet proposes using a convolutional cell to design a network, which was motivated by the structures of ResNet and Inception. NASNet predicts a small convolutional cell with a predefined shape, which are stacked on top of each other to form an image classification network. By adopting a convolutional cell, NASNet enjoys a lot faster performance than NAS. It also enjoys better transferability of convolutional cell trained on small resolution images to large resolution images. This transferability allows faster generation and training of image classification models used for large-scale images. NASNet employs two types of cells, normal cell and reduction cell. They both take in a feature map from previous cell or image and perform a series of convolution operations. Normal cell returns a feature map of the same size. A reduction cell returns a feature map with height and width reduced by a factor of 2. Each cell consists of b number of blocks. For each block, controller module selects 2 hidden units to use from previous cells or input image. Then, they apply arbitrary operations on each of the hidden units. The results are combined into one hidden state. This process, which makes up one block, is repeated b times to constitute one convolutional cell. Now let's look at the performance of classification model obtained by NASNet. NASNet A, NASNet B, and NASNet C represent 3 networks generated by the NASNet controller with different number of convolutional cells. This table compares the performance of the proposed method against SOTA hand-generated models on classifying Cipher-10 images. NASNet a model generated by the controller, performs better than all other models and achieves state-of-the error rate of 2.4%. These two tables show the classification performance on the ImageNet dataset, a much bigger one than Cipher-10. Note that NASNet A, B, and C are composed of convolutional cells trained on Cipher-10 dataset. They work well for ImageNet, even better than most of the existing SOTA classification models, showing that NASNet has great transferability. Second table shows applications on mobile devices, where the number of computations is limited to 1.5 billion. NASNet performs better than all other SOTA methods in limited settings, showing high flexibility. NASNet also enjoys plenty of room for application on other computer vision related tasks. Table on the slide shows application of NASNet A on faster RCNN for object detection. Compared to other faster RCNN using different SOTA classification models, faster RCNN using NASNet shows the best performance. In conclusion, this paper has given contribution of adopting convolutional cells on top of previous works on NAS. As a result, NASNet could achieve faster performance with higher transferability, achieving better performance than SOTA methods. However, this paper still faces the problem of computation power. Although it has lower computation needed to generate a model by almost 7 times from NAS, the method still requires 4 days of running on 500 GPUs to train. This is the end of my presentation. Thank you for listening.